Everything's going in the video? Okay. So welcome to the class. This is our CS 502 graduate class in algorithm analysis and design. So we're going to be studying everything that has to do with algorithms. Find out the important things about algorithms, what algorithms are, why do we need to study them. Nobody is going to hire, do people really hire algorithms designers? You know, why do we need to study this course? So first of all, what is an algorithm anyway? What's the purpose of algorithms? Who can tell me this? What's the purpose of algorithms? Somebody. Who has an answer? Is it up there? The answer sounded too good. Okay, so it's a, say it again louder.
Step-by-step procedure of dealing with problems.
Of what? Dealing?
Problems.
Okay, so step-by-step procedure, dealing with problems, solving a problem, resolving a problem, right? So that's what an algorithm is. Okay, what is an algorithm similar to? What else do we use algorithms every day for something?
An idea?
Like how do we use them? How do we use algorithms every day?
As a routine.
As a routine, okay. So maybe we get up, right? We brush our teeth. We make a breakfast. We get dressed. We go to class. So that's sort of a step-by-step, right? If we do everything in that procedure, then hopefully we have a successful day. We forget breakfast, or we don't brush our teeth, maybe we have a bad day. We don't feel good about it. So why are algorithms important? They're important in every day in our life because we do things the same all the time, right? But sometimes we have different problems to solve. So if we have a different problem, then we have to use a different what? Different algorithm, different approach, different solution, right? Okay. So an algorithm really is a solution to a problem, but it could be different instances of the same problem. We could have the same problem to solve, but the pieces, the details of the problem are slightly different. Right? For example, maybe an algorithm is we're going to get dressed to go out for the start of the day. That's the problem. Get appropriately dressed. But sometimes the temperature is very warm and it's 95 degrees outside and sunny, and sometimes it's minus 10 degrees and blizzard. So we're going to dress differently. So our algorithms are going to have some if conditions. If this is the case, we do this. If that's the case, we do this. If this is, right? So we have different, so we don't always come up with the same solution. An algorithm doesn't always come up with the same solution. Sometimes it comes up with a different solution based upon the nature of the problem, the parameters of the problem. Right? Let's say we have a set of numbers and we want to sort those numbers. So we decide that we're going to find out, are these numbers already sorted? So we look at the first number, and then we go to the second number to see if its number is increasing. And we continue moving forward as long as the numbers are increasing. At the very end of the number, we move beyond the numbers. What does that mean? That means that the data is already sorted, because every time we had the next number, it was bigger than the previous. So we moved. Even the last one was bigger than the previous, so we moved. Once we moved off the end of the numbers, we decided that the array or the data was already in order, correct? Okay, and sometimes we may find that maybe the data is not in order. So for example, let's say we're moving, but from here we stop. Why do we stop here? Because this number is not bigger than this one. Well, if it's not bigger than this one, what is it? No. Smaller or equal to? Oh, okay. So if we are moving, if it's bigger or the same, and then if it's not bigger than the same, then it's definitely smaller. So this number is smaller. But let's say we stop here, we mark this with a dot. And now we go to the next number, and it's again bigger, 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 bigger. So really, we found out everything was fine. There was a problem here, but this problem is also fine. So if there were 90 elements here, and 10 elements here, how many of the elements are definitely in sorted order? Not 100 because we did have to stop once, but then we could continue again. So how many elements are sorted?
99.
I'm not sure what you said there.
I'm sure you're not. Sure. Siri. All right. So the answer to the question is
99.
90 is a guarantee. Now this next element is smaller than the previous one, so therefore this is definitely not 91. But then they're increasing again. But are they increasing beyond the previous one or just beyond this one? We don't know. If they're increasing beyond this one, then actually how many elements are sorted? 99. So only one element is out of order. So let's say we go like this. So we have 100 elements and we go 10 elements and we stop. Why do we stop? Because the 11th element is not greater than or equal to. We mark it. We mark it. And then we mark it and we continue. And we stop at 20, and we stop at 30, and we stop at 40, 50, 60, 70, 80, 90, and we stop at 100. How many stops do we have? 10. Okay, so what does that mean about our data? Is our data less in order than when we stopped one time? Seems like it's less in order. Is it a lot less in order, or a little bit less in order? How much more work is it going to be to sort that data? Does it take more work to sort data that's really badly ordered
Yes.
than if it's only one element is out of order? Is that true?
Yes.
The answer is we don't know. The answer should be yes, but it's not always yes. And the reason it's not always yes, because the amount of work to be done to sort the data is dependent on the algorithm. If the algorithm doesn't take advantage of the fact that the data is nearly sorted and is not sensitive to that, then it might not care whether or not we have one element out of place out of 100, or whether we have 75 elements out of place out of 100. It might still do the same amount of work. It depends on the algorithm. So the algorithm is very, very important. Can you think of an algorithm for sorting that always does the same amount of work, no matter what the data looks like? Can you think of any? If the answer is no, don't say anything. But can you think of any algorithm that always does the same amount of work to sort data, regardless of whether it's already sorted, a little bit unsorted, or very badly unordered? Can you think of an algorithm like that?
Radix sort?
Radix sort, yes. Radix sort is an algorithm which will always do the same amount of work. So if it takes data which is already sorted, what's going to happen? It's going to sort the data, but it's going to do all the work as if the data was in the worst case. Right? Okay, so radix sort. Now, if you don't know what the radix sort is, talk to Jamie. She'll explain to you. She's an expert on radix. Okay. So now, what about any other algorithms that will do the same amount of work? Good question. Are there any algorithms that will do less work the fewer elements that are out of order? And if so, name one. So basically, what does it mean one element is out of order? That means basically what it is, you're gonna have every element is going to be basically fine. Increasing, 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 but there's going to be some problem here somewhere, and then it's going to be fine. So that element here probably should have gone here.
Mode.
Well, what does bubble sort do? How many people are familiar with bubble sort? Also known as my favorite algorithm, because it has a cute name. Bubble sort. So bubble sort works like this. So you have an array of numbers, right? A set of numbers, and starting with, this is index 0 or 1, 2, 3, 4, all the way down to n. So we have these numbers, and we put them in all kinds of crazy order, so they're not in order. But now we take the bottom two, and we say, are you... So we want the smallest here with the biggest here. So we look at the bottom two elements, and we say, are you in order? Meaning, is this element here smaller than this one? If it is, leave it alone. And then go to compare the next two. So you compare n minus 1. If it's okay, compare n minus 1, n minus 2. If you ever find that the smaller one is not on top, but the smaller one's on the bottom, you exchange them, and then you go up one element, and you keep comparing. So what's going to happen is the smallest element, wherever it is, so if the smallest element is here, that's correct. But if the smallest element is on the very bottom, it will be flipped once, twice, 3 times, 4 times. In fact, it'll be flipped n minus 1 times until it gets to the top. The smallest element will always be in the wrong place. So if it's on the bottom, it's going to go to n minus 1 position. Now when we compare n minus 1, n minus 2, it's going to go to n minus 2 position. N minus 3, n minus 4. Eventually it's going to go to 3, 2, 1, and it's going to end up here. So we know that a bubble sort, when we compare the pairs of numbers like this, we call this a pass, P-A-S-S, pass. When we do one pass, we pick the smallest element and we bring it to the top. Always. So if it's on the top, it's still going to be on the top. But if it's not on the top, it's going to get to the top. What about all the other elements? Well, it's not so clear what's going to happen to the other elements. The point being is if one element is out of place, will it be corrected by a single pass, a bubble sort? It appears that the answer is yes, but actually the answer is no. Why? Well, when I say one element is out of place, I was kind of fooling you a little bit. I was showing you that the smallest element could be already in place, so that's fine. But it could be lower, 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 lower. Wherever it is, it's going to get picked up. Right? But what if it's not the smallest element that's out of place, but it's the biggest element out of place? Now the biggest element belongs here. Correct? Because smallest to biggest, right? The biggest belongs here. But what if the biggest element actually happens to be here? So what's going to happen is, after I do my comparisons, I won't even look at that biggest element until the last comparison, and then that element's going to go down from position 1 to position 2. And what's going to go into position 1? The smallest element. Now the only problem with that, yes, we moved the first element into the smallest location, but because the largest element was at the top, it only moved 1 position down. How many more positions are left? N minus 2. Because this is 1, 2, and then n minus 2. These two are already done, and then below is n minus 2. So that means when next time I do this, I won't get to the biggest element until I compare 3 against 2, and then 2 will go into 3. So actually, how many passes do I need to get that biggest element down?
N minus 1.
N minus 1. It's going to start at position 1, and we want to end up position n, so it's going to go to 2, 3, 4, all the way down until we get to position n, so n minus 1. So even if one element is out of place, bubble sort could still require the maximum amount of work. And that's kind of funny, because basically, just think of the numbers. So think of the numbers like this. So this is 100, and then 1, 2, 3, all the way to 99. That array, bubbling up, pass after pass, will require 99 passes to sort the array, even though one element is out of place. Now, if the array is a little bit different, for example, let's say we have from 1 to 100, we start 2, 3, 4, 5, 6, 7, 100, and then we have 1. That will only require 1 pass. And only one element is out of place. So actually, it depends not how many elements are out of place, but which elements are out of place. It seems like the little ones on the bottom is good, but the big ones on the top, not so good. How do you describe that mathematically? It's kind of hard to know. What's the formula for that, right? So some algorithm. Now, there are other algorithms that work a little bit differently. For example, there's another algorithm that's called insertion sort. How many people have heard of insertion sort? Okay, 4 people. Here's how insertion sort works. It's also very fun. So instead of taking the array like this, we tip it over here. But it doesn't matter because arrays don't really exist, so it's okay. They defy gravity. So we have an array, and we're going to say the elements are element 1, 2, 3, tick, 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 all the way to n. So 1 to n, 1 to n. So what we're going to do is we're going to take element number 2. Not 1, element number 2. We're going to take that element out of the array. We're going to look at it, see the value. And then we're going to look at the element immediately in front of it and say, are you smaller, less than or equal to this element here? If the answer is yes, I'm going to put 2 back in. Because that means 1 and 2 are okay with each other. If I find that the element at position 2 is smaller than position 1, I'm going to slide position 1 into position 2. And I'm going to put the element in position 2 in position 1. So when I finish my comparison, I will have element 1 followed by element 2, or element 2 followed by element 1, such that they are in increasing order. Again, could be greater than or equal to, or it just could be greater than if you have unique numbers. So let's just kind of get the idea. So when I take the third element out, I already know that elements 1 and 2 are okay with each other. So therefore, if this element is bigger than the second element, what does that mean?
It is already bigger than the first element.
So it's also bigger than the first element. Therefore, what do I do with this element in position 3? Put it back in, and position 1, 2, and 3 are already good order. Right? Now, how many elements are sorted so far? Now, what is the smallest element in the array? Where's the smallest element in the whole array?
First.
No.
We don't know.
We don't know. That's the correct answer. Okay. Always, the answer to my questions is probably not the obvious one. And that's the way I like it. So the bottom line, we don't know. Because basically, the smallest element could be here, and when we pull it out, everybody's going to have to slide until we get this one in here. You get the idea? Now, let's think about our array. So when we did the bubble sort, we basically said what happens if let's say, what happens when the smallest element is on the bottom, which is here. So let's say we have a situation and the elements are all increasing, but the last element happens to be the smallest element. Then what's going to happen in that case, in insertion sort, is I'm going to take element 2, and what am I going to do? Put it back in. 3, 4, all the way to 99. But when I pick out element 100, what am I going to do?
No. We'll have to compare it.
Is it bigger than this one? No. Is it bigger than this one? No. No. I'm going to slide all these 99. I'm going to put it here. How much work did I do? Well, I had to do n examinations of the elements, and then I had to do n moves. So altogether, approximately 2n amount of work. So if I have 1,000,000 elements, it's about 2 million operations. How fast can I do it on a computer? Can I do that in a second or less? 2 million operations. Can I do 2 million operations in under a second? The answer is yes. Why? Why is the answer yes? Because how many operations I can do in a second is a function of what? The speed of the processor. And how fast are today's processors running in terms of how many operations per second?
2.7 gigs.
So these are 2.7 gigahertz. What's gig? What's the B word? Billions. So 2.7 billion operations per second. Now, what the heck is an operation anyway? What is an operation? What are they talking about? Comparison. So, but what is an operation? Could be a comparison.
1 line.
7.
When I have a statement like in a Java language or a C++ language, x is equal to x times 5 minus 3 times y. Is that an operation?
Yes.
No. What is that? That's a source code of, right? Source code of a language. That has to be what? Before it's executed.
Compare.
Compiled. Compiled to what? to machine code. Now, if I'm running C++ and I'm running Java, and I'm running those two languages on my PC, are they executing different instructions? One is the C++ E's, the other one is Java E's. Are they executing different instructions or same instructions?
Same.
Really? Same instructions.
Machine.
So they execute the same machine instructions, even though they're written in different languages. Yes? Are you sure? Yeah, see? You wanted to say yes, but it's too obvious. They are executing the machine instructions of my PC because that's the only language my PC can actually execute, which is machine instructions on the PC. Have you heard of assembly code? Assembly language? What's assembly language? Is that Java? No. Is that C++? No. Is that C#? No. What is it? It is the language of the machine. How many of you have taken a course in computer architecture or computer organization? Yet. Some of you have. So sometimes, so when you take those types of courses, and at some point you will, and you will say, wow, Professor Richter was right. I didn't think he was, but he was. When you study that, then you will study that basically there's something called the instruction set. So what is the instruction set? What do they mean? What do we mean by the instruction set of a computer?
Communication between registers and...
Okay, so it is the set of instructions that actually operates on the hardware of the computer. Ultimately speaking, that everything that executes on a computer has to execute on the CPU, correct? What is the CPU? CPU is made up of three major parts. What's the first part? Well, start with something that's some action. What do we have?
Processor.
We have the ALU.
ALU.
ALU is the arithmetic logical unit. What does the ALU do? It does the addition, the comparison, the subtraction, any logical. It does the if, equal to, if not equal to, if greater than. It does shifting, registers. It does bitwise and, bitwise or. It adds numbers together. That's what the ALU does. So it's the number cruncher and logic processor. So that's the ALU. Then we have to have the control unit, CU, control unit. And the CU basically tells the ALU what to do next. CU might say, hey, you need to feed this data into the ALU and this data into the ALU, and now you need to add them. And so when the ALU puts this in, adds it, there's a result. The CU says you need to take this result and put it over here. So the CU tells the ALU what instruction to execute, and by instruction I'm talking about something called a micro instruction. That's the instruction that actually operates at the hardware level of the ALU. And then it has to fetch the input from the ALU from some very, very small, tiny memory that's part of the CPU, typically on chip. And that memory is called what? Starts with an R. The registers. So the registers are a small set, maybe 32, maybe 64, maybe 256 memory locations. That's it. They are part of the CPU chip, which is next to the CU, which is next to the ALU, all part of the CPU chip. All that stuff is on chip. What makes this register so fast? Because it's very small, and it's very close to the ALU, and it's running at the clock speed of the CPU. So when the CPU goes 2.7 gigahertz, it actually means that if you take 1 over 2.7 billion of a second, 1 over 2.7 billionth of a second, you understand this is a very small amount of time, the ALU can execute one of its microinstructions in that period of time. Now, in order to do x is equal to x plus y minus z blah 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 times k, I may need to take that high-level Java instruction and I may need to translate it down to 7 or 8 micro instructions. Because the micro instructions are really moving data from memory ultimately to the registers, from the registers into the ALU, from the LU back to the registers. That's how the machine executes. Actually executes everything from the nothing goes into the ALU without going to the registers. Well, how the heck does it get into registers in the first place? Well, the first guess would be RAM, right? From RAM. Well, because RAM is fast. But actually, it doesn't come directly from RAM. Usually, it comes from an intermediate memory between RAM and the registers, which is called cache memory. C-A-C-H-E, cache. And the cache memory is a very powerful memory. It's much smaller than RAM, but it's a little bit faster than RAM, but it has one very special quality that RAM doesn't have. And that quality is that the cache memory is called associative memory. Have you heard of that, associative? So associative memory is memory that can be, you can search that memory all at once. So basically, think of it this way. Let's say you had 16 different colored socks. And for some reason, you always put them in different spots. So you're looking for your yellow socks today, and you have a sock drawer, and it has 4 drawers and 4 rows of 4 drawers, so you have 16 drawers. So typically you're going to say green, orange, black, yellow. Okay, now you can follow your dressing algorithm. So you get your socks, but you're searching the drawers individually. That's how we search memory. That's how RAM is searched. We search it individually. But what I am telling you is that associative memory works like this. It's like saying, okay, it's like having all of a sudden, instead of having 2 hands, you have 16 hands, and you pull out 16 drawers, and you see what's in there, and you take the yellow socks. So what does that add to you? Speed. Instead of 16, maybe we have 16,000 or 160,000 drawers. Pull them all out, look what you're looking for. So it's very powerful. Much more powerful than RAM, and just as quick as RAM, but there's a problem with it. The problem is if you're going to be searching the entire contents of a memory simultaneously, you need to interconnect all parts of memory within each other, so you need more wiring between the memory. And so what happens is, the bigger the memory, the bigger explosion of interconnections. The connections go at a rate of n squared. So if you have n is 100, 100 times 100 is what? 10,000. But if you have 1,000,000, it goes to 1,000,000,000. You see what I'm saying? So what happens is, if we make the cache too big, we explode the number of connections, which is one problem. And what happens when you have more connections? You have more electrons trying to flow through those connections, which means you generate more heat, which means you also generate more delays, because everything is now going to go slower. So if you make cache too big, you defeat the purpose of cache. You make it hotter, and you make it slower. When you make it just the right size, about a mega, something like a few megs or something like that, then you make it just the right size. So initially, cache used to be cache memory. So cache memory is sort of so what happens is whenever a CPU requires some instruction or some data, it goes always to the cache to see is it there. Searches the entire cache simultaneously, associatively. If it's not there, it goes to the memory. Memory brings it to cache. It goes to cache again. It brings it in. Once it's in, it stays in the register, and it can stay in the register until that register is needed again. When the register is needed again, it has to get written back out from the cache, right from the register, back into the cache. And it stays in the cache. And when the cache requires that memory, it has to be written from the cache back into RAM. It's a complicated process. It's a complicated process. Okay, so that's the way our computers are executing the programs. They execute in terms of micro instructions. But we were talking about a C++ program, a C# program, a Java program. Are they executing the same instructions? Well, no, they're not executing the same instructions, but yes, they're executing the same micro-instructions, because ultimately if they're going to be executing on my CPU, it's going to be my instruction set of the CPU, so ultimately my translators have to take the Java code and bring it down to instructions. Okay? And if it's C++ code, I have to bring that also down to the instructions. So ultimately they're going to be running micro-instructions in the same language. Ultimately that's what's going to happen. So that's the way that goes. All right, so algorithms are, we're getting back to this problem. Algorithms, so for example, if you take a program that's written in the Java language or in the C++ language, and you want to execute it, what do you have to do to execute it on as a micro-instructions set? You have to translate it. And the translation is done by something called, well, typically we think of a compiler. So a compiler is a translator. Well, what exactly is a compiler? A compiler is kind of an algorithm that takes input, which is the source code, and generates output, which is the object code. That's what a compiler is. It's a very complicated algorithm. In fact, we used to teach courses about that. And you're lucky we don't do that anymore, because it was a pretty hard course. But it was a good one. And so the whole course was dedicated to how do you translate. And that's a whole other story. How does translation done? And it used to be people were trying to find better and better, more efficient ways to translate. And I think we got to the point where we feel that the compilers are optimally solved. We know how they work, so we don't want to bother teaching you this kind of stuff because we figure, okay, that problem has been solved. Let's work on things that maybe haven't been solved yet. So that's why compilers are no longer taught, but they're still important. There's, if you have to generate new compilers, you have to know something about them. So now you have to maybe get a little more book learning. All right, so algorithms. We talked about the sorting algorithm. We talked about the insertion sort. We talked about the bubble sort. So sometimes an algorithm may have one element out of place, but still do the maximum number of work. Actually, if we think about it, we could actually solve that problem. If we take bubble sort, remember bubble sort used to take the data like this and go like this, we could solve the problem of the biggest element being here if instead of bubbling up, we bubble down. Because then the biggest element will always keep going all the way to the bottom. In fact, what we could do, we could have one bubbling go down and one bubbling go up. So if we had, for example, so we had the situation where we had the smallest element on the bottom and the biggest element on the top, this bubbling would take this to the top and move this one down one, and this bubbling would move it down, we'd solve the problem. So is that a better algorithm? What do you think? The answer is, I don't know. Define better. Define better. Because if something's going to be better, we have to be able to quantify it and say, it's better. Always? Not always. Sometimes? Yes. Okay, so what does that mean? What does sometimes mean? In real life, in practice, well, what does that mean? Random data. So we have to be very careful. Algorithms are very, very important because we want to improve them. And when we improve them, or we have better algorithms, we have to have ways of proving and showing that what we have actually is better, or in fact that it works. How do you know that an algorithm even works? I have an algorithm. How do I know it works? Well, we ran it 5 times and it worked. Is that a proof? No. That's not a proof. Because, watch this, here's my proof. I have a bubble sort algorithm, and I'm going to prove to you that bubble sort will sort where the number of passes is equal to the elements out of place. So what I did was I put one element out of place, I put the smallest element at the bottom, and one pass, and we're okay. I put the smallest element and next smallest element here, and it turns out 2 passes and it's there. So now I put 5 of the smallest elements here, 5 passes, everything is back to sorted. Is that a proof? No. Because if I put the biggest element here, and I only have one element out of place, so sometimes you think it's a proof, you think it's working because you didn't test it on fair data. You didn't really let the data be random. You fixed the data. You set it up in a way that's going to work for you, not because you're an evil algorithm designer, maybe, but because you simply didn't think that it might make a difference. So really, we should test our stuff on random data so that we don't fix and preset things so they work nicely for us, but in general might not be as efficient as we think they are. So we have to be very careful about how do we test algorithms. Okay, so one of the things that we're going to do is we need to make sure that an algorithm that we designed actually works. And we call that a proof. We say, we're going to prove that it works. But in order to prove anything, we have to be able to prove in general. People are very bad at proving things. They prefer to yell. They get louder. But I know it works! But speaking louder doesn't make it any more true. It doesn't matter how loud you say something. If it's wrong, it's wrong. So if you want to prove something is true, you have to use logic. You have to use some way of convincing people that can look at your logic and say, well, there you go. There's no fallacy here. Obviously, you went from step by step, and you showed that if you follow all these steps, then this algorithm, in fact, is going to solve the problem. You have proved it. So again, what is an algorithm? An algorithm is a set of steps. These steps must be finite. What does that mean, finite? They must be what? When I say the number of steps must be finite, what does that mean? What does limited mean?
Fixed set of something.
There must be some final number of steps. There must be a last step. An algorithm cannot simply get closer and closer and closer to the truth. And the longer it runs, the closer it gets. But I'll never get to the truth, but it gets closer and closer. That's not an algorithm. That's an approximation of something. Do we have an algorithm for computing the value of pi? No. But we have algorithms for what? To approximate number of pi's. Can I get the value of pi to 25,000 places? Yes. Is that very close to pi? It's very close. Is it pi? No. Is it going to work for all scientific computations, including building bridges? Yes, because it's very long, it's very, very precise. But it's not pi. It's an approximation. Let's face it. There is no algorithm to compute pi. But there are algorithms to generate approximations of pi which are close enough to work in all engineering applications, in scientific applications. But they're not pi. They're approximations. So let's get that clear. So if you're trying to prove that your algorithm generates pi, save yourself the time. And don't prove it. Because you can't prove it. Or just run it, show me what pi is, and I'll tell you if it's right. So algorithms, we have to be able to verify that they do what they do. We have to be able to prove things. And proving algorithm is really no different than proving anything else in our lives. I mean, to prove something, you have to be able to show that it's true at all times. So an algorithm must take a finite number of steps. It doesn't mean, now, what if finite is 37 trillion? Is that finite? Yes, it is. Finite doesn't mean finite but not too big. That's not fine. Finite means there is, for example, if I told you that to solve a problem of size n, where n is, for example, 1,000, I need to execute 36 trillion steps. And I can prove that it's true, then that's an algorithm. Now, in some cases, you may have an algorithm, but the algorithm, which is finite, then this finite number is so large that it would take you 50 centuries to solve the problem on the fastest computer. So it's an algorithm, but it's not a feasible algorithm because you can't run it. If an algorithm is going to take 50 centuries to finish a problem of a particular size, then what's the use of the algorithm if we can never see the result? So just because we have an algorithm doesn't mean we won't use an approximation. Because some algorithms, their amount of time to work is very, very heavy. very, very large, and it's not feasible for us to wait that long. When the input into an algorithm increases, and then the algorithm starts blowing up into huge numbers of operations, which can take, as I mentioned, many, many hundreds or thousands of centuries, then that is an algorithm, but it's not feasible. We cannot take advantage of it. But we may still need to solve problems that are based on what the algorithm accomplishes. We just have to look at different solutions. So if we don't have an algorithm, we have to use an approximation. What's the trade-off? What do you give up by using an approximation? Let's say the algorithm takes 50 centuries, but the approximation takes 2 minutes. Which one are you going to use? Approximation. So what are you giving up? What are you not getting?
Accuracy.
You might not get optimal result, but you will settle for maybe the best result you can get given the time. Okay? So we might not be able to get the optimal result, but we may be able to get a very good result. Maybe that's okay. Maybe that's sufficient to get a very good result. So that's very, very important. So the algorithm has to solve a problem, and I'm going to just say optimally. It must always be the best solution. It's a solution. It's a complete, total solution. Algorithm is a complete, total, successful solution in finite time. Okay? But again, the complexity of the algorithm, and that's what we're going to be studying, can be vastly different. The complexity of the algorithm isn't a function of the size of the problem. If we increase the problem, does the complexity change? No, the complexity doesn't change. But what changes if we increase the size of the problem? The time. For example, you may have a complexity which is linear. Linear means it's going to be proportional to the size of the problem. Linear. So if n is the size of the problem, then the number of operations that will execute on this algorithm will be Cn, where C is some constant times n. Okay? So for example, if n is 1 million, it could be 5 million, could be 10 million, could be 8 million, could be 7 million, could be 12 million, could be some C million. But if the problem goes to the size of 10 to the 18th power, then how long is it going to take me to solve this problem? Well, 10 to the 18th power, if C is 1, that means I will have to execute 10 to the 18th power operations, correct? And how long will it take me on my computer? Well, we said the computer can execute at 3 gigahertz, 2.7. Let's call it 1 gigahertz. So that's how many operations per second at 1 gigahertz? 1 billion micro operations. 1 billion. Well, how many operations do we have to execute? How many did I say we have to execute? What's the number? I gave you a number. I forgot what it was. Huh? 18 trillion? So 18 trillion? Let's say 18 trillion divided by 1 billion. 18 trillion is 18 times 10 to what power? 10 to the 12th. Over 10 to the 9th, which is billion. So what is that? What's 10 to the 12th over 10 to the 9th? That's going to be, so it's going to be 1,000. So 18,000. 18,000 what? 18,000 seconds. I don't know what that is, but let's find out. So I happen to have my calculator, also called an iPhone. So I have 18,000 seconds, right? If I divide it by 60, I get what? Number of minutes? If I divide it by 60, I'll get hours. So it'll take 5 hours. That's not very long. Well, to be honest with you, it's not going to take that many hours. It'll probably only take me 2 hours because I said 1 gigahertz, but it's really 3 gigahertz. But then I was talking about microinstructions first. So if 3 microinstructions correspond to 1 high-level instruction, maybe it'll take me 5 hours. Maybe it'll take me 6. Maybe it'll take me 5.8 hours. Maybe 4.7 hours. I don't care what it's going to take me. It's going to take me some number of hours. But what if our problem is not linear complexity? It's not Cn, but let's say it's equal to Cn squared. Now we got a problem, because now, remember I had 18 trillion. So, 18, so now I have to put my calculator sideways, so I can use the big numbers. That's the big number side. So 18, what did I say, 18 what? Trillion? So that's 18,000, 18 million, 18 trillion. And now I have to square it. 3.24 times 10 to the 20th power. And I'm going to divide it by the number of operations per second, which is also known as, I'm going to use 3 billion. I'm going to use 1 billion. I'm going to use 1 billion. 1 billion. 1,000, 1 million, 1 billion. Okay. So I have the number of seconds in here. That's the number of seconds. If I divide by 60, it's going to give me minutes. Divided by 60 is going to give me a number of hours. If I divide by what?
60.
Divide by 24, it's going to give me the number of. And if I divide by 365, roughly, it's going to give me the number of years. So roughly speaking, 10,000 years, 273 days. 0.9. 10,000 years. What time is it now? We have time for coffee. So that is an algorithm, but the problem is this algorithm, if it's proportional to n squared, we have a problem with that, because what happens is, as n is increasing, n squared is growing like this, like a parabola, but n is growing like this, linearly. So they're both increasing, but one is increasing in a linear way, the other one is increasing in a quadratic way. So as n is getting bigger and bigger and bigger, this one is growing, but still we can kind of see that where it's going, this is going to the sky and beyond, right? So we have to be very careful as to not just whether the algorithm is correct, but how efficient is this algorithm going to be? How long might it take me to solve a problem? And if you decide that, hey, I spent 2 weeks trying to solve this problem, and my best algorithm will take 20,000 years to solve it on our fastest computer, so I feel like a failure. But I felt like a failure, but then I read a book, and a book about algorithms, and it told me that this problem that I tried to solve, a lot of other people tried to solve the same problem, which is not really the same problem, but it's a similar problem that can be translated into the same problem, and they don't have any better solutions. That makes me feel better about myself. That means that I am no worse than the best. That makes me feel good about myself again. All right. So what we're going to be doing in this class, so the notes, I'm not going to start this, but we'll start this next time. But basically, we're going to be talking about some proofs, some logical arguments for algorithms. Then we'll go into complexity of algorithms. We'll go into some mathematical techniques for algorithms. Ultimately, the goal of this class is to put together code and mathematics. So when you look at one, you'll see the other. We want mathematics and code to be one and the same. And I know that you all have had some mathematics. Some of you love math, some of you not so much. The bottom line is we will do a lot of math, but I will teach you all the things and refresh all the math you need to know for this course. So all you need to do is just come to every class, study all the notes, and you'll be in perfect shape. You won't have any problems. We also will have some GAs that are going to help me with the class, but you will do fine. So the math that you will need in this class is math that I will teach here. We will do a little bit of algebra, a little bit of probability, a little bit of calculus, a little bit of this. Whatever we do, you're going to get a lot of experience over and over again, doing the same type of examples, so you'll feel comfortable about how to apply it. So ultimately, again, code, math, we want to see that they are really sort of, you know, it's a marriage. They're sisters, right? They're together. They are working together, and when you look at one, you'll see the other, etc. So you look at code, you should see math. If you see math, you should see that this is related to this code. Okay? That's our goal. and you're going to get there because I've done it before. I know you can do it. All right, see you on Monday. Oh, you got a 5-day weekend. All right, see you then. Bye-bye.